Thank you, Chelsea. Yeah, so that's a really long title. Hopefully we'll walk through it together today, and you'll understand why I had to make it so long and I couldn't make it any shorter. But first, I want to tell you all a little about me. This is my first time at SciPy, so I'm going to give a little introduction. Thank you. I got my PhD from the University of California, Berkeley just under a year ago. I did all of my work in radiation transport, so simulating radiation moving through space. And this was in collaboration with Oak Ridge National Labs, and a lot of my work was done as a member of the Berkeley Institute for Data Science. So I hovered around, kind of creeped on the BIDS fellows, but I wasn't actually a fellow. Now I'm at the University of Illinois at Urbana-Champaign at National Center for Supercomputing Applications, specifically in the Data Exploration Lab. There's a lot of members of the Data Exploration Lab here at SciPy this week. You might have seen Nathan Goldbaum give an update on YT, the package I'm going to be kind of talking about today. Yesterday in the tools plenary session, you might have seen Megan Lang give a talk on interfacing science models in using CIS interface. That was 2 days ago. Or you might have seen Kasper Kowalik give a talk on the whole tail. And I'm also involved in scientific computing. I'm a software carpentry instructor. I maintain the software carpentry Git lesson, and I'm a member of the curriculum advisory committee for software carpentry, and I'm a part of the committee for diversity, inclusion, and scientific computing on NumFocus. That's a lot of stuff, sorry. So we're in the data visualization section. All of us care about data visualization. And I'm going to be specifically talking mostly about a package called YT today. YT is a package that is designed to visualize multidimensional data. It was originally designed for astronomical data, but now, as Nathan mentioned yesterday, it is branching into other domains. So I've given a little selection of different domains that YT is branching into. Here we have meteorology, we have an original astronomy data set, we have high energy physics, and oceanography. This is like an earthquake simulation, and so seismology, and then also relativistic physics on the last one. So we can visualize our data, and when we want to publish papers, we want to get some really high quality images. But in between that, we want to interactively visualize our data and see where the interesting things are. And so this is a different step in the data visualization sort of pathway that we want to go down. Interactivity allows on-the-fly parameter tuning. We can change the color map to bring out features that interest us. We might change the min and the max values of our data that are being visualized because we are interested in them. But it also allows for this exploration of our data. We can zoom in on a feature that we care about, and maybe we see things that we didn't expect in our simulations or in our observations. This reveals the interesting science. And it also allows science to be accessible. We might have a data set that we want to share with the public, and interactive data visualization allows our science to be accessible to non-scientists, maybe to scientists that don't really like coding very much or find coding really intimidating, and also the people who are new to the data set. So these can be, I might pass my radiation simulation data to a friend and they don't really know it very well. Giving them an interactive tool to browse that data and visualize it interactively is very helpful to them. And there's a lot of interactive tools that exist in the Python ecosystem. We care about this. This is our community, right? So I'm going to be specifically talking about interactive visualization with YT today. YT has some interactive features already, but I'm going to be talking about the niche area where you're going to be having data maybe on a remote server or something like that, and you want to browse it on your local machine. So I'm going to do, like we were talking about the last one, I'm going to do a live demo, so we'll see how this goes. So I especially want to talk about how amazing the Jupyter widget ecosystem is. SciPy Widgets has developed a whole suite of tools that you can use to interactively browse your data in a Jupyter notebook. I'm going to show you, though, that this can be limiting sometimes. especially when you have larger data sets or if you have an image that's quite large or you're re-rendering things a lot. So I'm going to import, I'm using YT here. Is this also readable to everybody? Okay. You want it bigger? Okay. Whoops, sorry. Yeah, I'm trying it. Okay, I'll talk through it. I don't know why it's not zooming this time. Okay, so I'm going to interact. This first execution is I'm loading my data set. This is on my machine, and I'm going to be loading Isolated Galaxy, which is a data set that you can download with, that's in the documentation of YT. It's something that's used as, to introduce beginners to YT. So, yes, I want to download that. Oh, great. Huh? Oh, thank you. That was me leaning on it. Oh, I see what I did there. Thanks, everybody. There we go. Ha ha. Okay. Well, good. Now everything's going super well. So I've imported my data. I get some information from YT about my data set. And now I'm going to try and use Jupyter widgets out of the box with this data set. So I'm using a set of widgets to create, I'm setting some traits first. So traitlets are things that I can sync with Jupyter widgets, and you can use. So if you have a trait, you can sync it with one of the slider widgets or something like that, and it'll update. So I'm going to set up a visualization using these traitlets, and then I have an image, SciPy widgets image that I'm going to deposit my data into. Okay, so the first render doesn't quite work, but if I zoom slightly, the first thing here is supposed to be zoom, and then the next two widgets are X and Y. So we can see it's a very isolated galaxy. There's nothing around it. And if I start zooming and moving around, what this is going to do is I'm going to have to update the image, and I'm going to have to repixelize it to update the view if I zoom out. And if I do this, I'm going to let go now, and it's going to keep moving. And YT is printing some error messages, which is why now we have this extra box. But so if I go down, I can see that I've recreated this fixed resolution buffer. This is part of YT. It basically, the fixed resolution buffer will take a slice, and it'll create an array that is fixed. So if I have a data set that has a mesh that's variable, it's going to make it so it's all equal. So if I want 500 by 500 pixels, it's going to give me the array in that fixed resolution. So I have to re-update it every time with that new fixed resolution, even though I have a slice that I had already taken out. And I've done this lots of times. So you can imagine as you peruse your data set, you're going to be regenerating images lots and lots of times. So if you have a really large data set on a machine or even on your computer, this can be very slow. Okay, so I mentioned that this can be very slow. What's really happening when we start rendering images in a browser, but on our local machine or even on a remote server, we send a request from the browser to the machine, and then that's going to serialize the data, it's going to calculate the image, and then it's going to send it back, and we're going to pull that image down from this remote server onto our machine, and then we have a visualization. Super cool. But as I said before, you can do this lots and lots of times. So when might this become cumbersome? we have the total time to generate a single image on the server, and I've kind of selected a couple of different things that I think that you might spend time doing that. You have the signal, like the request signal to request this image, the time to serialize the data, the time to calculate the image on the server, the time to pull it back down into your browser, and then the time to display the image. But when you're doing it with this process, you have to do this n times, and all of these specific time variables are going to be multiplied by n interactions. So if I zoom, I might have like 20 images that are created in a zoom action if I want that animation with these data sets. So what if instead of sending the image back from the server, we send the request and we get a chunk of the data that interests us, and then we do the calculation and the display of the image in the browser. So we pull some of the data into the browser rather than the image itself. Pushing data to the client makes sense as if we can make the time to calculate the image on the client side smaller than the time to calculate it on the server side. So I've kind of condensed those small t's in the previous slide into two kind of big chunks that I think are interesting. So there's the number of interactions we have times the time. T-client is the time to calculate the image on the client side, so in the browser. And then we're going to add this with the time, the data, like how large the chunk of the data we're sending from the server divided by whatever our speed is. So if we have an extremely fast internet connection, this is going to be a very small component. But we want that in particular to be less than this. So the time to generate the image on the server plus the time to generate the time that it's going to take to transfer it. So the data divided by the rate to transfer it back and forth. And you can see that we've taken this n, and the number of interactions is only times the time to generate the image on the client on the left side. So I've kind of talked through those. So how might this happen? What are the big features that we think we can make that happen? First of all, I kind of mentioned, the more interactions you do, the more time you're going to be generating, you're going to be wasting transferring images from your server up onto your local machine or down onto your local machine. Also, as you increase the size of the image, this is going to get more and more cumbersome, right? Because this term over here is going to get much larger. And also, if we can decrease the time to calculate the image on the client side, that's going to make this a more beneficial transfer. So this is just an illustration kind of giving you an idea. If you have a data set that has this multi-resolution data, we can overlay what the grid looks like. And you can see towards the edge of the data, we have a pretty sparse set of data, but then there's some interesting regions where our mesh is much, much finer. Now, if we're going to be exploring this data set using a traditional method where you transfer the image every time you update, and if you want like a 10 by 10 pixel image, that's not going to be a big deal. But as in you increase the pixel resolution, you're actually becoming very inefficient because you have all this sparse data and you're sending hundreds and hundreds of pixels that are exactly the same value in these outer regions. So we created a widget that does this. Let's see if I can push plus in the right place this time. So this is the same data set. And we have some controls here. They go away. But this is actually a fairly large image. I've chosen a 1,000 by 1,000 pixel image. And I'm using SciPy widget's layout to shrink it down so it's not stretched weirdly during this interaction. So I can change the color scale to log. I can also change the color map to whatever I want it to be. And then I also can click in the image, and it updates way faster than if I was using traditional widgets. I also can drag it. And that'll update immediately. Whereas if I did a drag event like this, if I built this in purely on the Python side with the widget, it would be much, much slower. because this is very significant, transferring this 1,000 by 1,000 pixel array back and forth into the browser. So what does this mean? Like, we built this widget, it's cool, it seems kind of neat, maybe not cool as an awesome cat plot, but you know, it's pretty cool. But with a single fixed upfront cost, we eliminate the requirement to transfer all of those images between the server and the client. This is useful in some cases, but not all. So, you know, if you have a data set that's really dense and you have an extremely fast internet connection, then maybe it's not going to be useful to use this. But this is useful for a lot of different cases. So I'm going to kind of talk through what is happening. And in a little bit, I'm going to tell you more about WebAssembly. But so I'm going to tell you how the first render kind of works. So we have our data from YT. We send a couple of different arrays. PX and PY are the center points of each of those mesh cells that you saw. So you can see it's variable. And PDX and PDY are the half-width values of each of those mesh cells. And then value could be any field that you're interested in. It could be density, it could be temperature, or something like that. And I have a little key down here. So the yellow is going to be a function that we built in WebAssembly. This is custom. And then traitlets are things that we can, like you saw before, these are things that we can sync, and these are on the Python side. These are accessible to any user. So you could modify these as you wanted to. And then, so we're going to pass this in to our widget. It's called YT PyCanvas. And all of those arrays are going to go into a widget called the Fixed Resolution Buffer Viewer. This has two custom WebAssembly modules. There's a variable mesh, which is the data structure we store all of the data in. And then there's a fixed resolution buffer, which is like the view of the data that we're interested in. So we pull that like little chunk out. The variable mesh isn't going to change after we've uploaded the data. We're going to pass it into a data array. This is going to make a data array, and we're going to pass it to our normalizer. So we pass that array, and we want to do another performance important function. So we're going to pass it into WebAssembly again, and that's going to be COLORMAPs. That's the name of the module, but it's actually normalizing, and it's creating an image array out of the data array. So it's taking this single array that's all data points, and it's going to make it into this RGBA image. And then we're going to pass that image array back into the fixed resolution buffer viewer, which deposits it in a canvas and then renders the image. If we change the color map, I've now highlighted this in red, nothing upstream of this needs to change. So we don't actually have to interact, we don't have to interact at all with the variable mesh or the fixed resolution buffer because we didn't change where the view was. So what this is going to do is going to send the data array back through the COLORMAPs WebAssembly function. It's going to change the image array and the rendered image. If we do a canvas interaction, though, we're going to be moving the fixed resolution buffer around in the variable mesh. So the view width, this is if we change if we zoom in, then that's going to change where the fixed resolution buffer is. That's going to consequently change the data array, the image array, and then the rendered image. So I had just mentioned that we did this stuff in WebAssembly, but I didn't really say what WebAssembly was. So WebAssembly is what a lot of the web is built on. It's a language that's supposed to work seamlessly with JavaScript, but it's the performance important parts of the web. So instead of using JavaScript and serializing to JSON all of our data, we can put it directly in WebAssembly if we build custom WebAssembly modules. But because WebAssembly was designed with interacting with JavaScript in mind, these two can seamlessly interact together. We also have a sandbox memory environment, so all of our calculations are going to be done in the browser, and it's not going to happen anywhere else. And this reduces that T client that I talked about in that equation earlier. And why Rust? Well, so you can compile into WebAssembly from a lot of languages, from C or C++. So I've never programmed before this in Rust or JavaScript, and Rust was extremely approachable. It had a pretty low time to get up to speed. It was super fun. I didn't expect that. I don't know. And it's performant. It's designed with compiling to WebAssembly in mind. So to do this, to create our functions in WebAssembly, we can annotate our, this is in Rust, so we can annotate our functions with this wasm bindgen, and this is saying we want to make these functions available to JavaScript from WebAssembly. Then when we compile that, we get an automatically created JavaScript file, and this is kind of what that structure, data structure, is going to look like when exposed from JavaScript. Another package that we found very useful is wasmpack. So this actually compiles all your Rust code into WebAssembly and then packages up in a package that you can put on NPM. So it's super easy. You just upload it, and so none of your users really have to deal with compiling to WebAssembly from Rust or anything like that. They just get to download the NPM package that's associated with it. And this is actually me compiling our project on my machine. And there's some cute emojis that are also included, which is pretty cool. So I have a demo of a larger data set. I just showed you like a sample data set from YT. So we have a couple of different things here. This in particular is from simulation of a population 2 star, which is like the second generation of stars that's formed after the really light hydrogen helium-based stars. And I'm loading this in. The original data set, so I mentioned that we're taking chunks of data. The original data set is several hundred gigabytes of data. We pulled a slice down for this particular chunk. So if I do the log, I can see this data set. I can also change the limits so it might be a little easier for you to see. Maybe. And I can do the same thing just before. So the slice is quite a bit smaller than the original data set. But this is, because we made this into a widget, we can also leverage all the functionality of the widgets. So we can link, for example, another field. I've plotted density here. But I can link it. There's another field in this particular simulation of temperature of this star forming. So I'm going to first create a slider that allows me to see things in log scale, because I know this data set is very sparse. And then, so I want to zoom in really far, and then I'm going to create a temperature one as well. So let's see what happens. Okay, so let's say I decide, okay, I really hate this color map on the other side. I've now linked the fields on both sides, so I can do a log and we can see both of them, and this looks pretty cool. These are really different. But I can change the color map just using the traitlets, and then I can move these around as well. And I can click to a new center that might interest me and do that. I also can use a projection. So YT has tons and tons of really interesting ways that you can explore your data that haven't been accessible in this directive and interactive way. So this is doing everything I just did in one giant cell. So I'm sorry, it's like very much a wall of text. And it's going to take a little bit because I'm doing a projection instead of a slice, which actually collapses all of the data and brings out features from all the dimensions. I've been showing XY slices so far, but this is trying to pull out some of the Z dimensional data. Okay, so I have this, and these are pretty interesting. So let's say I think this is a pretty interesting part. I can start zooming. And this goes way faster than if I was doing this with anything else. If I was doing this with straight Python. I wouldn't be able to do this, and I wouldn't be able to interact this easily with my data set. Oops, sorry. So we do have some limitations of this widget. It requires a 2D data slice. You just saw that. I kind of talked a little bit about it. So we can't fully interact in 3D yet. And that's not a trivial change. So that's something that we're hoping to do in the future. There's also potential limitation for data sizes. I've shown this. I've shown like some pretty large data sets, and we haven't like reached a limit, but it exists. And we have limited functionality. This is nowhere near like the ability of a lot of other interactive tools, but this is the first that has WebAssembly that we know. I'm almost in. And it requires maintenance in multiple packages and package ecosystems. This is non-trivial and can be kind of rough sometimes. And it's still really early in development. Moving forward, we want to broaden the functionality. We want to make it so it's even more intuitive for users to use. We're going to build out functionality with YT. YT has all these cool features that we're not exposing yet. And we want to restructure the widget to enhance performance even more. There's some links. I'm going to tweet the slides to this talk, so if you're really interested afterwards, you can go. These all link to everything you're interested in. And I want to give Louis Erber shout out. He gave a poster on restructuring some of your backends from C to Rust, also here at SciPy. And you can install this very easy. We have, as of this morning, we have this widget on PyPI. And you don't have to compile to Rust. And I'd like to thank the following individuals. Matt Turk really helped me with this. Nathaniel Clausen did a lot of the early feasibility studies of this work. Nathan Goldbaum and Castor Kalvalik helped me debug a lot of things. I'm just going to let you know that debugging in 3 languages sucks. Also, Britton Smith, he supplied the data for these larger the POP2 data set, and Katie Huff, who is my great friend and listened to the practice talk for this. And I'd be happy to take any questions.
Great, so I think we have time for one question.
Yeah, thank you very much. Great talk.
Thank you.
Yeah, you talked a lot about the application side of it, the programming. But as a user support or a consultant, my worry is usually about the network, the memory. So how much does the memory count in serving as a bottleneck if you are computing from the HPC, from the server versus the client? And how much memory do you need? Because all the manipulations you were doing, that you're doing with the widget, how much memory do you need? And at what point do you have some sort of bottleneck?
Yeah. So I have not done a full benchmark of when we reach a bottleneck. We know it exists, but I don't have something off the top of my head for that. I will say that this very large data set is a pretty good example of the types of data sets that people would be interested in. So we're pulling that slice down. That slice, we saw the projection was several hundred megabytes, and that was directly in the browser. But I didn't pull a full 3D data set into the browser, so I don't know exactly what the limit is yet.
And maybe one more question, if anyone has something. Yep.
Thank you for the nice talk.
Thank you.
Question about transferring the data between JavaScript and the WebAssembly, and doing it for scientific data and scientific data types and big arrays. Do you have any thoughts or ideas on how to do that, the best way to do that going forward?
So actually, because Rust and WebAssembly WebAssembly and JavaScript are designed to work together, we're actually just passing the pointer of the WebAssembly data through JavaScript. We have we're using clamped arrays. We don't have the serialization to JSON. So it's actually very friendly to transfer the data between JavaScript and WebAssembly. The hard part is getting it down into the WebAssembly in the first place. Did that answer your question? Okay.
Okay.
I'll be at the sprints tomorrow also if any of you have any questions or want to play around with this or something like that.